Welcome. This video will discuss ways to do curve sketching with techniques that you have not learned in advanced functions. So techniques of advanced functions would not be enough in this particular example that we're going to do. Because we have a function here that is a square root multiplied with a linear. So it's a combined function by multiplication. For the ease of this discussion, I have put down the derivative and second derivative for you, so I'm not going to show those calculations. So we'll start off by looking at the original function, and we're going to do this whole list from our algorithm. So first of all, because this is not a rational function, there's nothing that cancels, so there would be no holes. For y-intercept, you can substitute x equals 0, and you'll get the point 0, 1. For x-intercepts, we're going to sub in y equals 0, and we get -1, 0, because this part right here becomes 0 when x equals -1. And the other point is -1/3, because this part here becomes 0 at that value. Now, in terms of behavior, is going to be linear near the x-axis at this point, because this factor has an exponent of 1. And this particular one, it's a start of the domain, because we have a square root. We cannot put negative values into that input of the square root. So about the domain, because we do have an even root, we know that radicand has to be greater or equal to 0. When you solve that, you would get domain has to be greater than -1. In terms of our end behaviors, the edges of the graph would be where x equals -1, and the other edges at infinity. So as x goes to -1, we can find that it approaches 0 by just plugging in a really tiny number for x's in here to see where it approaches. And you could also do the same thing for this end behavior. You could plug in a huge number. You'll see that y also goes to a huge number. In terms of the horizontal asymptote or oblique asymptote, that usually will occur when you have a rational function. But because we have no denominator, we don't have any vertical asymptotes or horizontal asymptote or oblique asymptote for this question. Okay. Symmetry of the function. As we know, functions could be odd, even, or neither. So if you recall from before, if we put a negative on the input, so meaning reflection in the y-axis, and we get the same thing as a reflection in the x-axis, that would have been odd. And that doesn't happen here. If you plug in -x on the inputs, you'll notice that it's not the same thing as having the overall function being a negative. If this reflection in the y-axis was actually equal to the original, that would have been even symmetry, but we also see that that's not the case here. So this is neither. Next, what we're going to do is figure out whether the function lies above the x-axis, positive y value, or below the x-axis. What you want to do is split the intervals using zeros and VAs. So as you can see, they are placed here on a number line in the order that they would appear. Next, what we want to do is figure out what the sign is on each of these intervals for each portion. And then once we have each portion filled in, we want to know what it is overall for the y value. So first of all, you'll know that these values are not in domain, so we're going to scrap them out. If you were to plug in any number in between here, you will always get a positive under the root, because otherwise it would not be defined. So it's positive for both of these intervals. For this particular one, the values would be negative for any x's below this -1/3, but positive after. You can even visualize a line for yourself with positive slope to fill this in, or you could actually try some numbers in between these and plug them into the x to see what sign it is. Then this chart, by the way, only works if these two things are factors. Factors means that they have to be multiplied between each other. Because if they're not multiplied between each other, then you cannot say positive times a negative is necessarily a particular sign. But with multiplication, you can do so. For addition, subtraction, you cannot. So just make sure that everything is factored for you to be able to use this chart method. And so multiplication, positive times a negative is a negative, positive times a positive is a positive. So overall, we know that this is the places where the function touches the x-axis or zeros. And the meanings of these positives and negatives are the following. If it's a negative, the y value means it's below the x-axis. And if the y value is positive, that means it's above the x-axis. And so what we can do right now is sketch what we do know so far. We have these 2 points from the zeros, we have the y-intercept, and we know our end behavior at the edge there. Now from the original function, we can't actually tell if there's a lot of wobbles that would happen or turning points that would happen. So this is actually not how it's going to look, but so far from what we've showed so far, this is a possible graph that could match that. It is not correct because we have to continue on with the calculus topics which deal with the derivative. So I'm going to take that away because it's wrong. And let's continue on. If we have the first derivative, if it's not given to you, then you would find it. We're going to find critical points from 2 places. One could be horizontal tangent that comes from the numerator, and the other ones will come from the denominator. So if you solve when this yellow part is equal to 0, you'll get x equals -7/9. And because we're supposed to plot them, I converted them to approximate decimals. And the way I found this particular number right here is I plugged this into the original for the x's, and I got approximately -0.63. Now, because this critical point came from when the slope was equal to 0, that means this will have a horizontal tangent at this point. So this red line shows this horizontal tangent potentially being there. From this information, we could have horizontal tangent at a saddle point. However, that would imply that there would be another turning point because it has to come back around to touch this x-intercept. But we know that there is no other critical point that has a horizontal tangent, so this can't not be the case. So that's a way. It could be something like this. It could be maybe with a cusp. We don't know that yet, so we'll continue using calculus strategies to figure that out. Or it could be something like this. So let's continue on to decide what is it. Looking at the denominator, we can find out where the derivative is undefined or does not exist. These points could be vertical tangent values where the tangent is actually specifically infinite slope. It could be a sharp point if this was piecewise graph, or it could be just values that are originally not in the domain. Now our domain here doesn't have the denominator, but it does stop at -1, so that's the reason why it will show up here as well. So x is -1 is one more critical point, but we already know that this is the start of the graph and it's not a vertical tangent type of graph there. Next, we're going to do a table one more time, but this time we're going to place in the factors of the derivative on the inside and again fill it in. Notice I'm starting this table from -1 because below it we don't have a domain even. So if you were to take any value in between this, so any x value and plug it inside here, it'd have a negative, and above it will be positive. Here it will be exactly 0. For this particular one, I put a little infinity symbol to remind myself that this came from the denominator, and it's always positive on this portion. Again, to fill in what the overall signs for the derivative are, what you want to do is multiply negative times a positive and you would get a negative, and positive times a positive is a positive. What does this mean? Always go back to what does it mean for the original function y. Derivative being negative. Another word for derivative is slope. Slope being negative implies y is decreasing, and here it would be increasing. Then we can classify these critical points using this first derivative test. We already know that x equals -1 is just the start of the graph. In this particular one, if you imagine we have something that's falling, then it's flat, horizontal tangent, and then it's increasing, it's going to be a minimum turning point. And so that first or the last guess that we had that is supposed to go like this was the correct guess. However, to finish off the graph, we still don't know other pieces of information. The graph could go this way or it could go the other way. This will be indicated to us by the concavity of the graph, which involves the second derivative. So we don't know this part, so I'm going to erase it. And we'll continue now with the second derivative. All of these steps, by the way, are just summarized in an algorithm. I'll do another example that shows all of the steps at once. So from second derivative, you're going to find possible inflection points. They are found by looking at the derivative when is the numerator equal to 0 or when is the denominator equal to 0. So we find the two values here. We cannot say they're actually inflection points yet until we do some checking. So one more chart. This time we'll place these possible inflection points on the number line in the order that they would appear. But you'll have to remember that these values here are not in the domain. So you cannot say that this is an inflection point because it's not in the domain. And then as before, you fill in your signs and it ends up being always concave up. And so you can finish off your graph here by drawing it always concave up. The conclusion is that there are no inflection points because inflection point only happens if you have an actual change from concave up to concave down or vice versa. And then this particular step says you can classify critical points using the second derivative, but we've already classified those using the first derivative. So in our next video, we can talk about how to do it with this other method. And as always, what you want to do is, if you have the ability to check using technology, this is a picture from Desmos. If you type in the original graph into it, you'll see that our sketch is right on.